Good morning. I'm Arun Rao, and after having an exciting insights from Dr. Kiran Majumdar Shah, who spoke on challenges and the opportunities for Indian pharma industry, and also Claire sharing details from industry to life, it's now time to get insights from an industry expert on medical devices. So please welcome Dr. Ramanan. Uh, every day, medical device companies face the realities and responsibilities of developing, manufacturing, and commercializing innovative products. To be successful, companies continuously need to balance cost, value, and time to market in producing products that are safe, easy to use, and are at right price, while also complying with extensive government regulations and reimbursements. This, in addition, the feedback from patients, healthcare professionals is becoming more and more important in developing new technologies. So, my guest here, Dr. Ramanan, I'm really delighted to have Dr. Ramanan Lakshmi Narayanan, the Chief Technology Officer of Sajanan Medical Technologies. Dr. Ramanan is an architect and inventor of Supraflex screws, the stent which has gained the industry reputation as most deliverable coronary stent for complicated artery license of the heart. He is a mechanical engineer with masters in design technology operations and a doctorate research specialized in robust design as and Six Sigma. Dr. Ramanan is an alumni of IIT Madras and BITS Pilani. He carries over 40 years of accomplished expertise spanning multiple products, studied patients with patents and publications. He is also an inventor with passion for medical devices and affordable healthcare. So, welcome, Dr. Ramanan. First of all, I would like to congratulate you and your team on putting Sajanan Medical Technologies, an indigenous medical devices company, on the world map. We are really proud to learn that SMT's Supraflex stent product line is currently being used as a global industry benchmark. Could you please tell us about the journey of the stent, the release, and what role simulation has played, sir?
Thank you, Anurag. It's a great feeling to be the part of this event and share the views about what the products, what we build, and to share the thoughts on the coronary stent, which is most important and a safety critical aspects to save lives. Before I step into my presentation, I would like to say the origin of Sajanan Medical Technologies, which has come with the thought of noble idea and a noble cause, saying that, when in 1990s, when nobody was talking about make in India or produce in India, any of these, not even slang, Mr. Dheeraj Lal, today his daughter Dheeraj Lal, he was engineer. He specialized in the laser cutting manufacturing. He sees the difficulties of patients who are going through in India and the cost of the stents. He thinks that why not I do that when I'm cutting the laser with diamonds? Why not I cut a metal? So that is the whole thought of the noble idea with which Sajanan Medical Technologies 1990s was born. Today, we spanned across the country. That's a sapling what he has planted with that idea. And today, we spanned across all the pools of the globe. And shortly, we will be entering into US market. Let us see what the stent and what we are talking about in the cardiology segment as a product. And let us first look at the situation of coronary stent. All of us know about the stent. And let us have a quick overview of how to reach the stent, how to place the stent, what is stent, and why it is necessary. There are two pathways through which you can enter the heart. One is this pathway. This is like our taking our car and reaching to a location, or through another one location where I can take the different route and still reach the destination. This is the femoral path, what we call, when there is an incision which is being made at the groin, where the entire catheter is being driven through this entire path and reaches the heart, not inside. This is the outside. Like if you look at the heart, this is the inner portion of the heart, and this is the whole of the heart. The aorta through which the catheter comes in, these are all the arteries, what is available on the screen too. So if there is a block, when we talk about a block or a cardiac attack, and there is a calcification, and the flow of the path is getting controlled, and where the flow is restrained, so there is when the flow is restrained, the heart as muscle cells at the below these locations start dying. When the heart cells start dying and it cannot pump, eventually the heart as a pump will not function. So that is where the emergency conditions comes in. That is where the stent is extremely, extremely useful in recovering the patient. That's what our pledge is. We will save millions of people. Already we have saved close to 2 million people across the world with our product and the stent. So what happens when this entire catheter is being driven inside the heart? This entire stent reaches their location. The doctor sees only on the radiographic images once the cut is being made, once the incision of the catheter has been made. That's how he reaches. Once he reaches that location, based on the blocks, he decides to expand the stent. When the balloon expansion, this is what happens. There is a balloon which is the driver which carries the stent, and it expands. And when it is expanding, the metallic part of the stent, this is what the stent, we call it as elephant stent, because the stent is very small in size. This I use it for my lectures and classes, where the stent is bigger in size. It is a metallic tube. So this gets expanded. And once the expansion happens, the plaques are being pushed, and the balloon is being shrunk, and the entire catheter has been driven out or taken out. The stent remains at that location. So either you reach the targeted or diseases artery location through femoral path or through a radial path. This is easier path. Some of the doctors specialize on that. I know Dr. Tejas Patel is the world's authority on radial access artery. Why people do this is the blood loss from femoral artery will be larger when compared to radial artery, and radial artery size is very smaller. The healing will be faster because we are puncturing a pressurized line. It is going to have its own time for blood to get arrested. Now let us look at the question of, okay, what we have talked about, the fundamental thing of a stent and a stent driving it across. There are two different elements onto this. One is the stent delivery system, and another one is the stent itself. We have seen in the previous slide, we are taking through the entire groin from where I am reaching the heart, or from the radial path, I am reaching my heart to stent it. So when we do this entire delivery system is a fragile shaft. It comprises of many number of components. In automotives or in any of the mechanical systems, we always talk about joints. Here also there are a lot number of joints are available, which are all thermal fusion. Here there is no welding, they are all thermal fusion. This is a polymeric material, this is a steel material. This is the balloon, which you have seen in the previous slide. When I was talking about this carries in the initial condition, this is to be very, very small in size. That is what we call it as crimping. The stent, which is 1 millimeter, 1.2 millimeter as a tube in diameter, which is being mounted onto this acts as a carrier. Then once the reached target, like doctor only knows about these two locations, which has been marked as radio opaque marker. At that locations, he goes and sees, okay, this is the location where the plaque is, and that's what he sees. At that point of time, the fluid is being sent across. We call it as contrast, and this entire thing which is being sent inside, the balloon expands. As the balloon expands, the stent gets deployed. The challenges, what are all the challenges? If you have seen how the complex the path was to navigate at all the curvatures and stuff like that, that's the biggest complexity. So how will I make the stent more deliverable? It combines with the two components, both the delivery system, which is a carrier, which is the car which is taking the stent to go and leave the passenger, which is the stent, at the target site, and he does the work, what to make the patient to be comfortable. So the stent is also contributing. If the stent is going to be a tube, normally people use cobalt chromium as the tube. That is, it's a solid tube in which the design matters a lot. It has to flex at different locations of the curvatures of the artery if it plays a vital role. It is not also playing the vital role. This entire catheter, which is 1.5 meters in length, when somebody is below the abdomen, the groin has been cut. From there, doctor is reaching to the heart. Then it has to take across all the curvatures. So that should also be flexible. So these are the complexities onto the delivery system and the component. Look at this. This unique design, what we have today, that is only because of that we call it as, the stent is more deliverable. And, that is the benchmark in the world today. So when I talk about the, what it makes to, the stent to be more flexible, there are many number of design elements. If I keep the thickness, that is one of the important criteria, the stent width and the stent thickness. In our stent, it is 60 micron. We are the lowest, thickness in its stent. We call it as ultra thin stent. So that gives the flexibility. Okay, if we were making the stent much more thinner, 60 micron thickness is close to our hair thickness. So when we are making it as that thinner, then the stent will be more flexible. Good, excellent. But what will happen when I have to go and, when I have to go and say the stent is to be expanded and placed, then this is the part of the simulation which you are seeing it on the screen. The stent is getting expanded. Now, at the clogged location, the stent is expanded and placed. If the thickness is very small, what would have happened is the stent will collapse. It will not provide adequate radial support or radial strength to push the, the calcified locations of the artery and keep it expanded so that the flow happens. So this is the beauty of it. You have to have a trade-off between the tube or to cut. You are seeing the differences between these two lines. This is the leftover material. I am taking 1 mm length. If I am talking about implantation of 16 millimeter stent, most of the stents carry about 12% of the metal. 16 mm diameter of the tube which I have taken for its length. I have removed about 84% of the material. I have left about somewhere around 12 to 13% or 16% of the metal is what is left out. So the design matters a lot in terms of how it makes it flexible. So this is one of the examples in an artery of the patient, which is called shepherd crook, which is the most tortuous artery. You see that this is what is the diseased vessel. In the diseased vessel, all the way he has to pass through all the curvatures, and here, this is where doctor has to implement. He will keep on pushing from the other end, which is 1.5 meters away from the location. So if the doctor is not able to send the catheter inside and the stent to the target location, what will happen is he will not be able to implant. So what will this stent has done is, in this is one of the benchmark of shepherd crook. We talk about this diseased artery is not treated. The heart muscles will die. If the heart muscles are dying, the patient has to be, laying his life. So after the stent has very beautifully migrated onto the entire location, doctor without difficulty, with ease, he has navigated and he has deployed. You can see the blood flow after the implantation. This is the beauty of it. We will talk about this into the part of, regulations. That is, that is one of the good thoughts what will be coming in. So,
that was my question that you were going to be.
Yeah, please.
In fact, excellent demonstration of the capabilities. But, Dr. Ramanan, most of the medical devices companies have to strike a critical balance between the cost, quality, time, and also there's so much of pressure with respect to the regulatory compliance as the stipulated governing bodies basically ask us to do. So could you please share your thoughts on the role of simulation in accelerating the regulatory decision making?
Excellent question. Thanks, Arun. Thanks for asking that. The point is, the moment the stent as a best stent, which has been conceptualized and it has been, brought as a prototype, tested, and stuff like that within the lab, still it gets implanted onto the patient as a first stent, first in man getting implemented or implanted. It will be taking close to 3 to 4 years easily, out of which there are many number of tests which is need to be conducted. This entire stent of superflex screws design, what has been done is completely through simulation. USFDA, for example, that is the highest standard the world looks at, above CE and other stuff. Like always, we know what is the limitation, what is the time frame which will be requiring. Say, for example, when the stent is being implanted, it has to work without any collapsing or it is failures for 10 years of its carried life. That is what the regulation needs are, which means that there is an blood pressure which is happening. There is a fatigue related loading which is happening once the stent is being implanted, because there is a flow. All of us know what is the systolic and diastolic pressures in terms of the artery gets in. When the artery is, heart is pumping and there is 80, 120 is the number most of the people will know who are not having blood pressures. What happens is, the stent, we talked about the length. In an artery, when it is becoming very complex like this, or in an artery which is having a longer lesions, 16 mm. See, we have the stents, the lowest stent length is 8 millimeters to longest length is been 48 millimeter in length. The minimum diameter of the artery to treat is 2 millimeters to maximum diameter, which is called the left main, where we will be taking in. There is a tapping from the aorta. From the aorta, that is where the supply comes in. That is normally 4 to 4.5 millimeters. These are all the variants what we have. But when it is being implanted, it may not be sufficient. In a lesion is larger. Very recently, I have seen a case in the right coronary artery. He has to place a number of stents. So that will be overlapping. One stent which is to be overlapped with the other. I'll just to show you the animation. See, when it is talking about the overlap, this is the first stent. This is the outer portion which you are seeing as the artery as a model which has been made as hyperelastic material model. And this is the nonlinear material model. It has got all the contacts. You are seeing now the second stent is getting implanted in it. So there is an overlap. With this overlap, the stent which is to be placed in a curvilinear locations, there is a bending which is happening. Then there can be a sliding. If the sliding is happen, then what will happen is the artery will get injured. That should not happen. So we study in terms of the overlap what happens. Apart from it, this is also being subjected to diastolic and systolic pressures. Like that is the pressure due to the blood pressure what is happening. And then I have 3 different variants. I cannot have like in the same diameter. When I'm talking about 2 to 2.25, I have one stent design. The design, if you see the pattern, that will be the same, but it is a different diameter. From the material with which it is being used. From 2.5 and to 3.5, I have one segment of the stent, which is called a 6-crown design, which will have 6 different loops and stuff like this. Onto the stent, if you are seeing this is what is called the struts. This is a 6-crown design. And on a higher side, where the main artery, that is what is normally called as left main, from where the entire blood starts supplying to the artery, that will be somewhere around 4 mm, 4 to 4.5 millimeters. So what FDA looks at it, if at all, if I have to look at if there will be a fatigue failure, and then I have to do real life fatigue testing for 10 years. Each one of the samples which is to be tested, it will be taking about 6 to 7 months easily on the test bed to find it out whether it will be a fatigue fracture will happen. If I wait for this to see whether there will be a fatigue failure and after that start redoing the design running like this, nothing will happen. So regulations today talks about, run the simulation. From running the simulation, find out the worst condition. From the worst conditions, identify which design you want worst of the worst, take across to the fatigue test. And simulation is a part of the accepted criteria with the regulatory authorities, including USFDA and other part. This is the beauty what we have, and this is where we were able to. Arun, it is not out of place to tell you and the entire audience, this entire stent, which has been scratched to the conceptualization today, where the stent is getting implanted across the world, it has been done in the computer modeling. Within 3 months of time, we did have all the iterations, about close to 35 to 37 models, which we have done, based on which the final stent has been made. And I'm proud to say I'm an inventor of that. That is the first pass design. When we made the first, prototype and tested for the in vitro conditions, we passed it on the first pass. There is no changes which have been made. That is the level of simulation that has helped out into the stent design. Does it answer your question? Then probably we can talk about the
delivery. In fact, that was also going to be my next question, with respect to how SMT developed a hemostasis device in the shortest possible time, specifically for dorsal procedure in coronary stenting. I think you spoke about it, but is there anything more that you would like to share on this, Dr. Ramanan?
Yeah, before I talk about that, Arun, I will also talk about the delivery system. We talked about the stent. I will stand on the slide for, this is the test track. We have seen on the human body how the test track is, how the different conditions in which it goes. See, the diameter of the tube, which I have shown you in the earlier picture, which is the carrier, is 0.6 millimeter. That is the OD of the tube. And, the wall thickness of the tube is 80 microns. This is the tube. At the end of this, if you see this, at the end of it is what you are seeing. This is where the stent is being carried out. So when the stent is being carried onto that, what is happening is, here, this is the location where the stent is being carried. The entire catheter goes to the different artery. So it has also to be flexible. This entire catheter design it has got the long slender shaft. It has also been made with all these type of simulation. So we have today has got a best part of it. So there is a contribution from the delivery system as a whole. We have our own benchmark studies in terms of that. And since the shaft is very slender, it is subjected to kinking. We developed the shaft through the animation. It is a dedicated shaft. We have our experimental validation to this close to 95% to 98%. This is the type of correlation what we are talking about. And this is how it helped in all the process of its development. Now, this is the benchmark. When we are talking about most deliverable stent, I have all the competitors on this part. This is what a supraflex screws is all about. The lower the force which doctor is experiencing during the tracking for the stent to reach the tortuous artery and to the target site, this is what is the products which are all available in the market. The product names are being, the respective manufacturer's name has been quoted here. This is Ultimaster, this is Arcedo, this is Zion Sierra from Ammar, Zion's Expedition from Ammar, Resolute Onyx from Medtronic, and Synergy from Boston Scientific. These are all the requirements on the test track what we have, and this is the requirement of the force. Lower is the better force. This is the benchmark studies. But doctors also say, today I had inputs from France. That's the first stent which has been implanted in that country. The doctor was so happy that it met across on a complex artery. And taking this question which you have just asked me in terms of the hemostasis device, in the first slide we talked about two different exercises to reach the heart. One is the femoral part. Some of the doctors who reach through the radial portion, radial artery is smaller in size diameter because of the blood losses are very minimal, and healing is easier. Dr. Tejas Patel, whom I referred in the first slide, is the world's authority on radial procedure. Today, doctors also keep doing the research on to minimize the blood losses and the recovery time. She is the practitioner of a dorsal plasty, which means now the puncturing is going to happen at a location of closer to the thumb. At that location, the puncture is happening. He touched my hand and said, what is the beauty of this devices? Okay, once the puncture has been made, the catheter is driven, the stenting has been done into the heart, and the catheter has been withdrawn, and this artery has to be closed. It is to be closed, the leak has to be avoided. So he has, when this was invented by him, he was telling me, he called me and said that, Ramanan, I want a device, he just pressed my hand like this, and he was telling me, I want a device like this. This is the pressure. So with that pressure, what is that? What we'll do? The beauty of the pressure is the artery, if it is overpressed, the blood flow to the thumb will not continue. If the blood flow to the thumb is discontinued, then the thumb has to be amputated. So there should be a smaller amount of flow, which is also to happen, but at the same time, the artery has to be pressed in such a way that like the healing happens. That's the beauty of this device, and he is happy having that design. Like simulation played a very vital role in terms of that. We have patents on both the stents and catheter systems onto the hemostasis devices too. We have patent applications filed. That's a happiness what it is. Like in the International Conference on Radial Cardiology Conference, which is called TRICO, and he has demonstrated during this launch and stuff like that. So that is the part of the answer what I have wait for you, Arun. What you have asked on hemostasis device. It's a very shortest span of life.
No, thank you so much, Dr. Ramanan. I think I just have one last question and just 1 minute because of the time constraints. With the current COVID situation, there is a lot of things that has changed for many medical devices companies. So, what do you think is the outlook in context of manufacturing, digitization, processes, as well as the R&D for the medical devices companies, Dr. Ramanan?
Excellent question, Arun. As far as the COVID conditions are concerned, from that point, what people are, said during this part of COVID is, all of us will make ventilators. When we are talking about, there are different type of ventilation. In the terms of ventilation, when we talk about the simplest model is volume control ventilation. The volume control ventilation is the one product in my life, 40 years of service. This is about 10 days within which we have had the entire part of the product built to an actual model. The beauty is there are a number of walls onto this. How much is the volume which we are projecting it? I cannot project all the volume, pumped it across into the heart of the lungs of the patient, and he will be suffocated. What is the doctor has to have a control in terms of volume control, what he is applying based on the patient conditions. See, an example of that is, the simulation related to the angle of rotation. I need to have the actuations which is to be done. This is the same part of the, the actual product where the actuation happens, and the simulation helped us out in terms of making it across. So in every part of R&D and to the manufacturing, the biggest part is we need to get on to get the product early to the market for the conditions which is needed to help out the people. The concept under the whole thing is help the people at the earliest time, make the people comfortable, save the lives. That's our fundamental thoughts. With that being said, Arun, we live our entire pledge, our mission, vision is pledged to save millions. We have already saved close to 2 million people across, and we are looking at the aspects of it where we can continue to save millions of people and increase the number of millions. That's what I have to share with you guys within this conference. Simulation is the best way to get the product early to the market, to meet the regulatory needs and everything. You can always get a first pass product. That's my message to Arun. Is there any other question I can take it across? Otherwise, thank you so much for the opportunity.
So thank you, Dr. Saravanan. We at Dassault Systems firmly believe in our vision that the platform, PD Experience platform, and our solution helps our customers to harmonize product, nature, and life. And I'm really very, very proud to be associated with Sajanan Medical Technologies and with yourself, Doctor. And we wish you all the best, and we continue to work together to bring to help you bring the next generation of products. Thank you so much, Dr. Ramanan.
Thank you, Arun. Thank you so much. Pleasure to have a talk with you. Thank you.
Thank you, Doctor.
Bye-bye.